I want to start by thanking the organizers for this wonderful event. I mean, I feel already very at home here. People are saying wonderful things, important things, and I think we should have one of these at least every year. So great job. Today, I'm going to talk about Struphy, which is a software package that we are developing at Max Planck since 2019. And so here you see the people that have been contributing to this project over the last years. And a big thank you goes out to them. So they have done an amazing job, and I will try to convince you of that. So let's start right away. What is Struphy? So Struphy, first of all, it stands for Structure Preserving Hybrid Codes. Okay, so I will clarify that later, what we mean by structure preserving and what we mean by hybrid. In essence, it's a Python package for solving geometric partial differential equations. It's open source with an MIT license. You can check out the repository. It's on our Max Planck GitLab. So you can access the code, you can fork the code, you can download the code, you can install Struphy. But however, if you want to contribute, you still need to ask a Max Planck employee for an account on this GitLab. So you should write an email to me in case you want to contribute. But okay, so that's another thing. Other than that, it's completely open. The code is entirely written in Python. Therefore, it's object-oriented. And then you might say, okay, how can you solve PDEs in a meaningful time with a Python implementation? Well, that's because of another open source project called Pixel. And I think Pixel was presented already today by Emily in a previous session. Pixel is a transpiler of Python code. So what this means is you write Python code, it gets then translated to either C or Fortran. You can choose. Then it gets compiled, and the .so files are then bound back into your Python code. So that's awesome. You can stay completely in Python, but get C or Fortran speed for your kernels. So that's what makes our Struphy project actually possible, I would say, this compilation step. On top of the compilation, we also have parallelization in the form of MPI and OpenMP hybrid. The Struphy project is very much curated, documented, and easily accessible via an API. So what do we mean by structure preserving? This relates to the methods, the numerical methods or algorithms that we use within Struphy. So this means in essence that after semi-discretization in space, where time is still continuous, we should arrive at a system of ordinary differential equation that has a sort of Hamiltonian form. You see here, Z are the degrees of freedom, which can be very, very many. So think of them as finite element coefficients, particles, that sort of thing. J is a Poisson matrix, so antisymmetric matrix satisfying the Jacobi identity, and H is the Hamiltonian of the system. So you have this J dot grad H term, which constitutes the Hamiltonian character of the system, and then you have a Q term, which can account for dissipation and other mechanisms. But so this Hamiltonian structure is, I would say, found in many plasma models. Many models that you very well know and maybe already use have this Hamiltonian structure. And in Struphy, we make the dedicated aim to preserve this structure also on the discrete level. This leads to more robust and more stable schemes, actually, that we see in practice, especially for long-time nonlinear simulations. So almost all models in Struphy are derived, that are in Struphy have this form, and you can get to this form by either discretizing a Poisson bracket, clever discretizing your equations, or by discretizing a Lagrangian. So it remains still the time discretization after that, and there you might choose to break the structure again for the sake of better performance, but you can also use things like symplectic integrators to really have a Poisson integrator for your full PDE system. So that's a little bit the philosophy of Struphy, to use these state-of-the-art numerical methods on plasma equations. So let's talk a little bit more in detail about the algorithms that are available and for which Struphy provides abstractions that you can use to solve your own models. Okay, so there are two big classes of algorithms basically for which we provide data structures. The first one is Lagrangian particle methods. There we have two categories: particle in cell methods or meshless methods, or smooth particle hydrodynamics, SPH methods. So in both of these cases, what you actually do is solving conservation laws of the form that you see here on top of the screen, with a flow velocity u that can depend on f and a possible source term. We can solve these kind of equations with our particle methods in arbitrary dimensions, I would say, and also in curvilinear coordinates. Okay, and the way you do this is by making the classical particle ansatz for your solution f. So if you have a density f, you discretize it as a sum of Dirac measures. The second numerical method that is provided within Struphy is a finite element framework, which is a sort of geometric framework called finite element exterior calculus. And therefore, we use yet another open source package. So you see, within Struphy, we already integrate open source quite actively, which is PsyDoc, also developed at Max Planck Institute. So here's the link to the repo. It's a very well-written repo that provides the finite element spaces that we can use then in Struphy. So essentially what we use is a discretization of the 3D de Rham complex that you see here. On top you have the continuous spaces, and on the bottom the finite dimensional subspaces that constitute your finite element spaces, and then you have projections into these spaces. So all these things that you see here, the gradient operators, the projections, and the basis of these finite element spaces, they are provided within Struphy in 3D. For these two algorithms, we have parallel data structures and solvers, and we are working on the GPU offloading of the kernels via OpenMP at the moment. So skip the references, you can read through them later. The finite element spaces provided are high order, so you can go high order if you want. And they have this finite element exterior calculus. We also will not go too much in detail. I just want to say that these are state-of-the-art finite element methods that are based on degrees of freedom that mimic a little bit the geometric meaning of your unknowns. So you can do a so interpolation for zero forms in the first space, a mix of inter and histopolation in the middle space, H curl and H diff, and histopolation in the third space. So if you do that with tensor product B-splines to build your finite element spaces, you can arrive at discretizations that manifestly mimic analytical properties such as curl grad equals 0 and diff curl equals 0 on your operators exactly. We also have a module for polar splines to treat O points. This is especially useful in Tokamak and stellarator experiments, where if you use curvilinear coordinates, you are in a toroidal geometry, and in a poloidal plane, you will always have a singularity, which is the O point, and the tensor product finite element bases usually perform poorly there. We have a solution for this. We provide a polar spline basis around the center, which leads essentially to continuous functions on the physical domain. Okay, so far a little bit about the methods that are available within Struphy. And so now let me talk a little bit more about the API and how you can actually use Struphy. So Struphy is object-oriented, and it provides many classes from which you derive objects for solving the PDEs, like particles, finite element fields, operators, solvers. You have mappings, you have MHD equilibria, and you have interfaces to other codes, as you will see. And so from all these objects within Struphy, they can be combined in the sort of Lego approach to create models, okay, that can be then run by other users. So models is a specific base class also in Struphy, the Struphy model base class, which guides you when you want to write a new model for your system of equations that you want to solve. So for example, we could check out in a Jupyter notebook the kinetic models that are at the moment available in Struphy. You can import the kinetic modules and then look the kind of classes that are in there, and you see we have, for instance, mods like Vlasov Ampere for one species, Vlasov Maxwell for one species, or also a drift kinetic model. So we not only have kinetic models, we can also check the available fluid models. We have actually 4 categories of models: kinetic, fluid, hybrid, and toy models. So if we check out the fluid models, you see also models that you might know, like cold plasma, linear MHD, nonlinear MHD in a variational formulation, and also viscoresistive MHD. Then you also see here an Euler equations with an meshless method, SPH method. So these kind of, the number of models will continuously increase. And we hope to have at some point all the relevant models for fusion applications within Struphy, actually. That's the goal. Now, how is the time stepping coded in these models? This happens usually via time splitting scheme. So you don't advance all your quantities within one step, but you split your PDE into subsystem. And then you solve just for the variables of the subsystems in a clever way, which is probably structure preserving. But this leads to smaller systems that can then be solved kind of in sequence. And this is a splitting scheme. And one such splitting scheme is always carried out by a propagator, which is yet another base class that is provided by Struphy, where you can implement your splitting substep. So for instance, we could look at the propagators that are available for fields. So for finite element fields in a variational framework. So you see we have a lot of, so here's a density evolution, entropy is pushed, magnetic field is evolved, momentum is evolved in a variational formulation. So we have at the moment, I think, between 40 and 50 propagators available in Struphy, and those can be combined fairly easily to yield your new model maybe, right? So you can build in a Lego system from these propagators new models. Like we have Poisson solvers, Maxwell solvers, these kind of things. Also for particles, we have a propagator. Let's look. So for instance, we have push eta. Eta is the logical space, so the position space in Struphy. This is just a position update. Within the push eta propagator, you can choose many different algorithms like Runge-Kutta 4 or discrete gradient algorithms, sorts like that. Implicit algorithms, or many different options are available. We also have guiding center pusher algorithms for particles, diffusion, and many more. Now let's come to the API. All Struphy objects are designed to work in curvilinear coordinates. So therefore you can run all the things that you have seen so far, all the models, all the propagators in mappings that are also available in Struphy and to which we will add in the future, or you will add in the future, hopefully. So for instance, we could import domains and then load the holotorus, okay? And then look at it, how it looks like. Now the holotorus, there's a lot of keyword arguments you can choose. For instance, one of these keyword arguments would be straight field line coordinates. If you set it to true, you get straight field line coordinates. There are many more keyword arguments that you then can check out for each individual mapping. There is also interfaces to other open source projects like the desk equilibrium code out of Princeton. You can load a desk output here with the desk equilibrium class of Struphy and then look at the mapping that is provided by this equilibrium, for instance. So this is the W7X test case of desk. You not only get the mapping, you actually get the equilibrium solution. So VMAC++ from the previous talk would be a candidate for another interface into Struphy, definitely. Now, installing Struphy should be easy, I hope. So you should do this in a virtual Python environment because there will be lots of packages installed and you should not mess with your existing Python environment. You can install the newest release from pip, from PyPy, or you can get the source code from the repo. And after you got the installation done, which by the way, you should have a working MPI environment for this to go through. So you should try pip install MPI for Pi. If that works, you're probably good to go. And after you install Struphy, you have to compile. And this will then do this pixel compilation of all the heavy compute kernels so that you can run at Fortran or C speed. If you see problems with the installation, there is a troubleshooting page in the documentation where there are some hints of how you can maybe solve problems. Now, how to use Struphy? Basically, we aim to operate in this paradigm from that we can do prototyping and production run in a single framework, in a single Python framework. So The way I would suggest how one can go about this is first you get familiar with the Struphy objects that I just showed you via the API. So we have Jupyter Notebook tutorials available in the repo and also in the documentation that you can try out. You can run yourself. You can do a Poisson solve, a diffusion equation, some particle solves. Once you're familiar with these objects, you can actually build a Struphy model, which is also documented. There's a lot of abstraction going into that help you in building new models. Then you can test your model with in the command line. So there's not only the API, you can actually run Struphy from your console, okay? And then, for instance, you can test your model. And once you're happy with your model, you can actually do an HPC simulation right away by adding a batch script, okay? What you can also do is use Struphy for teaching activities. So there are very basic models implemented that are useful for lots of students, I guess, that want to get into fusion physics. So you can maybe use this in your lectures. Now let me show you an example how to use the API. If you want to push particles in a magnetic field, let's say we go in a cylindrical geometry, make an instance of the hollow cylinder, and then we load the particles class, since we want to push particles. Let's say we want to push 20 particles. We have to prescribe boundary condition in the 3D domain. And yeah, then let's instantiate the particles class. Then we have a particles object, which holds all the data structures and lots of information. So we can draw our markers. If we just do this without any options, we will draw randomly, but uniformly on the domain, our 20 markers. Now, what we need is also a magnetic field. So let's import an equilibrium. The simplest one is the homogeneous slab equilibrium. Let's set we want to have a B field along the axis of the cylinder that we just defined. So this was the Z direction. The equilibrium is then this homogeneous slab object, and it needs to know the domain. So we pass the domain to it. Afterwards, we also want to build a de Rham complex. So we import the de Rham class and specify our resolution in the 3 directions. So the number of cells, the spline degree, and the boundary conditions. And then we instantiate a de Rham object. So there you have now all the de Rham finite element spaces and operators and projectors and so on available. And this we did because we want to project our MHD equilibrium, which is the object equal, into the de Rham finite element spaces. And this is done by the projected MHD equilibrium class.
Hey, Stefan, sorry to interrupt, just to let you know that you're at 17 minutes.
Okay, I'll hurry.
Just.
Very good. So now we import 2 propagators. We want to push in position and in V cross B. We pass the information that we have on the domain and the de Rham complex to these propagators and instantiate them. And then we do a time loop and do a sort of strung splitting. So here you see the splitting algorithm. We passed our particles object to these propagators. So the propagators need to know what they should update. We run the loop, we do some plotting, and you can see the particles in our cylinder. They nicely gyrate around the magnetic field. And all these objects that you have seen in these notebooks, they are actually MPI parallelized and can be used also in HPC applications. So the same things you use in notebooks, you can use for HPC application. So applications, particle classifications, for instance, that is easily done. You can do this on your laptop. You can do Landau damping. These are input files are provided. You can test this right away. You can also test Euler equations, a gas expansion example from our meshless methods. So this is done with the typical SPH velocity update. So there is no mesh needed. This is drawn from Monte Carlo. We can also draw the markers on a regular grid from a tessellation, and then you see you have much less noise. So these are simple examples to get into Struphy and to learn how to use some objects. So last slide, this is how you can build with Struphy. I think you probably will need some initial support to get into how to use it. You can get in touch with us. We will help you to get into the workflow. You can learn the notebook tutorials. You can try to implement your new model, a propagator. You can follow the development on the repo and really benefit from the growing Python ecosystem for fusion research and embrace open source. Thanks for your attention.
Brilliant. Thank you very much, Stefan. Yeah, so we can open the floor up for some questions. And I also just wanted to know, I really appreciate the idea of kind of being able to both run this code on a laptop and on a HPC system, because I always wondered that with some of these giant codes where I can like bug fixing on a laptop is bad enough as it is, and I can't imagine what it must be kind of trying to debug some of these codes that need to run for days and you have to queue up to get them on the clusters and such. So yeah,
Right.
I really like the idea of that. So we have one question at the minute from Jonathan. So how does the polar spline basis compare to the Zernike polynomials as a basis function for the poloidal plane?
Yeah, that's a very good question. So the Zernike polynomials are quite similar. The difference is that Zernike uses a Fourier basis in one direction, I guess, in the theta direction, whereas the polar splines are built from tensor product spline basis. That's the main difference. But you could achieve the same thing with Zernike polynomials. Yeah, correct.